Okay, so today again we begin with another lecture, which is it's continuation of the previous lecture in which we talked about non-crystalline solid structures, mainly glasses. So we'll just finish that part in this lecture, and we'll start a new topic on polymers, structure of polymers. So let me just give you a brief recap on what we talked about. So we introduced the topic of structure in non-crystalline solids. And here mainly two categories we are going to talk about. One is the glasses and second is the polymer, because many of these materials, glasses don't have any long range periodicity, and polymers again most of the polymers don't have a long range periodicity, they have short range ordering possibly. So these materials, so we started with glasses. Glasses are mainly based on SiO2 units, and it is the and the silicon is basically tetrahedrally coordinated. So it depends upon the sharing of oxygen atoms between tetrahedras, what kind of structures silicon oxide can give rise to. So there are plenty of structures that we looked at in the last lecture, depending on the coordination of oxygen atom. It can make a completely 3D crystalline structure as well, which is in the form of quartz, if all the tetrahedras were beautifully arranged in a hexagonal fashion. Now, so you have basically this kind of arrangement. This is that silicate tetrahedra. So these are all corner of the tetrahedron. At the center of the tetrahedron you have silicon ion sitting. So it is essentially the arrangement of tetrahedrons, which governs basically how what kind of structure will be formed. So we add impurities like sodium and calcium to glasses because they can break this network. And so, for example, you might have situations like this in which you have a tetrahedra, and since it has 4 corners which need to be satisfied, silicon, this for example sodium or potassium or calcium can attach themselves to these corners, satisfying some of the bonds. As a result, you have no longer this condition of having to satisfy 4 corners. So as a result, the structures that you might form may look like something like that. So for example, you have a you no longer need a 4 corner sharing. As a result, you might have things like these. Okay, so and in one of them you can have let us say a sodium linker. So this sodium linker can possibly go here as well. So you can see that you can satisfy some of these corners using sodium linkers. So you don't necessarily have to go through so can remain. So you no longer need. So they may remain arbitrarily coordinated in the 3D space. They don't have to follow a hexagonal pattern. So you might have, so this might have correlation in some other direction like this. This might have correlation in some other direction in this fashion. Again, you might have a sodium atom here, and so on and so forth. So this can have relation with another this thing. You can have a sodium here, and so it doesn't need a basically a 3D network to continue to make the structure. And the angles are arbitrary as well. So you have a random sort of network with branches all over the. You can have something like that. I have one sodium here, let us say, and so on and so forth. So, you can have a sort of breaking of tetrahedral bonds. As a result, you do not necessarily have to have four-fold coordination with 4 tetrahedras, and this basically allows. So, what does it result in? It results in breaking of a 3D network. As a result, it leads in. So, basically, the bonds are broken, and this results in lowering of Tg and Tm. So, these basically they introduce weaker bonds in the network. So, easier melting at lower temperature, allows for the formation of shapes at lower temperatures. So, there are a variety of these glass modifiers which are put into the system. I will show you some compositions in the next few slides. Now, the next thing, the silica can also make a random network where hexagonal network will be maintained, but it will not be ordered, it will not be hexagonally ordered. So, for example, you can have a pattern, so you can have a situation like this, in which you have a fused silica or quartz structure in which there are no impurities, it is 99.8, 99.9% pure silica. So, basically it is a glass which consists of silica only, but in amorphous and or non-crystalline form. So, here you can see that you have each oxygen atom. So, these are silicon atoms, these ones, and these are oxygen atoms. So, each oxygen atoms are shared by 2 tetrahedras on the sides, and then one on the there will be one on the top as well, right. So, they make a hexagon, they make a network in 3 dimension, but it is not a hexagonal network, okay. And this, so they do satisfy the requirement of each oxygen being coordinated between 2 tetrahedras, they do satisfy that requirement. However, that requirement does not take place, does not get fulfilled in an ordered fashion. As a result, you form a structure which does not look like a hexagonal network of tetrahedras, and hence this form of silicate glass is called as fused silica or basically fused quartz, okay. So, it does not have a crystalline structure, it is used for a lot of applications because it is cheaper for applications which require high temperature softening. So, this has a relatively higher temperature of softening as compared to your sodium or potassium or calcium substituted glasses. So, wherever you, so these are used as for instance, so this fused silica is basically you can say it is a tetrahedral network formed in an unordered fashion. So, there is no hexagonal pattern there, but the requirement of coordinations are fulfilled, and these are, so they have relatively higher Tg. So, they soften at higher temperatures. As a result, they are used in so higher, its softening temperature is about 1600 degrees centigrade. So, to be precise, at 1665 is the softening temperature Ts. So, as a result, these can be used for applications which require high temperature. So, they are transparent. As a result, they are like glasses, but they can withstand very high temperatures. So, for example, windows, refractory applications, and since applications which require low coefficient thermal expansion because they have higher softening temperature, their coefficient of thermal expansion is lower. So, application requiring lower coefficient of thermal expansion. So, this is the 3D network of the tetrahedras, not arranged in an ordered fashion, but in a disordered, but in an unordered fashion. So, there are typical glass compositions which I will now list. So, there are some glass compositions. First one is Pyrex glass, which is a very well known name that you might have heard of, Pyrex glass. This contains 80% silicon oxide, and it contains 14% of boron oxide, and it contains 4% of Na2O, and this has a softening temperature of around 550 degrees centigrade. So, this is something which is used in laboratories quite extensively, where you require the material to withstand its form until about 400-500 degrees centigrade. So, Pyrex glass is something that we use in our laboratories. Chemists and material scientists use it quite extensively. Then we have Vicor glass. This Vicor glass is it contains 96% silica and 4% boron oxide. This softens at about 1100 degrees centigrade. So, higher than Pyrex glasses. So, any temperature where you require even higher temperature stability, you use this boron substituted silicate glass. And then typical window glass that we have, window glass is basically 9% calcia, 4% magnesia, and 14% Na2O, 1% alumina, and remaining silicon oxide. This has a softening temperature of about 120 degrees centigrade. So, it is useful for only low temperature applications, all right. But it can be formed in shape into shapes very easily at lower temperatures. As a result, it is very popular glass. And then of course, you have fused silica, which I showed you earlier, which is 99.9. So, fused silica is essentially 99.8% SiO2. Okay. These are the non-crystalline structures that we have. So, basically you can say that glasses are, now in summary you can say that glasses are ceramics with lack of long range periodicity. Yeah. Okay. They contain same attributes as of ceramics. They are hard. They have so they are hard, harder than metals. They have lower coefficient of thermal expansion, provided you use them below the softening temperature. Okay. Than metals. Below Tg or Ts than metals. They are transparent and color can be tuned by putting impurities. Okay. And they are of course insulators, thermal and electrical insulators, and then they have their melting point Tm or Tg. Melting point of glass transition temperatures, they have different definitions in the glass sense, but it can be tuned by modifying the composition, and as a result by, so basically the elements that you add are called as glass modifiers. such as sodium, calcium, boron, these kind of materials, these kind of elements. You can see that typically the elements that you are putting have valence lower than that of silicon. Okay.
What is the use of this glass transition temperature?
Glass transition temperature you need to know because this will determine at what temperature the glass will soften. So, it is basically an indicator of softening of glass. So, wherever it's useful from the perspective of forming shapes, what kind of temperatures you need to use. It's useful from the perspective of determining the service temperature of glass. Suppose you want to use glass as a window, and if glass has a transition temperature of 50 degrees centigrade, then it's no use in this country, because the temperature reaches in this country, surface temperature can reach as high as 60-70 degrees centigrade during summers. So, depending upon the type of application, for example, if you have a furnace or vacuum chamber wherever you have some high temperature phenomena going on and you want to put a window there, that window cannot be a low temperature glass. It has to be a high temperature softening, high glass transition.
Same as softening temperature.
Sort of, yeah, glass transition temperature is indicator of softening temperature. We move to next class of materials, structures, which are basically you can say structure of polymeric materials. So, we will start with a new topic, structure of polymeric materials. Now, polymers of course are very important, as we know. They are used in variety of applications. So, they basically contain elements which are light elements, which are carbon, hydrogen, nitrogen, or in some cases oxygen as well. So, polymers, as we know, they are basically contain light elements, which means they have low density. So, they can be used for weight reduction, okay. So, which allows you to have weight reduction, okay. Then they have excellent corrosion resistance, okay. For example, HF cannot be stored in glass bottles, it can only be stored in plastic bottles. So, they have excellent corrosion resistance, and they are cheap because they can be formed at lower temperatures, the processing is easier, and can be shaped into various forms. In fact, 3D printing nowadays, which is a very important manufacturing method which has revolutionized manufacturing, polymers can be 3D printed very easily. So, 3D printing is something, so basically they have 3D printability, and they have lot of other attributes such as they are electrical and thermal insulators. And the bonding they have is basically they are mix of covalent and secondary bonding, right. Secondary bonding could be your hydrogen or van der Waals type. So, these are certain attributes of polymers, and and there is an interest in studying polymeric structures, what kind of structures they have. So, polymers basically predominantly these are all non-crystalline materials. So, if you look at the name polymer, poly means many and mer means basically a basic unit which gets repeated. So, basically these are they contain various units of mers. So, one mer is attached to another mer, is attached to another mer, and this process goes on for thousands of units, and they make a basically chain. So, this is basically a polymeric chain, which is typically covalently bonded within the chain. But if you have many such chains, one chain, second chain, third chain. So, the chains are covalently bonded, but between chains you have secondary bonding. So, this secondary bonding between the chains allow it to be flexible. There is a flexible in the structure of polymers. So, basically there are now, depending upon how they how these chains are arranged in space, the polymers could be a linear polymer. So, you can have a linear polymer, which is also called as chain type structure. So, basically it requires that monomer means one mer, okay. Arrangement of monomers in a chain in a curvilinear fashion, okay, so like this. And then you have what we call as network polymers. These network polymers have arrangement of monomers in a cross network in 3D. So, there is a crisscrossing. So, you have these, so they are branched in 2D and they have also branched in other dimensions. So, they basically a branched cross-linked network in 3 dimensions, you can say cross-linked. Okay. So, let me now define polymers. There are, so these polymers typically are characterized as, the first category is known as thermoplastics, and the second category is known as thermosets. Okay. Thermoplastics have generally thermoplastic, okay, they can be softened. So, they soften with temperature, with increasing temperature, okay, with increasing temperature. So, they have a sort of melting light phenomena, they melt at very high temperature. So, and followed by melting, okay. So, they can be formed in various shapes, just like a liquid metal is casted into solids. They have very little cross linking between chains. So, if you have chains of polymers, there is very little cross linking. So, you can say very little cross linking. You can say cross linking, okay. And then they are typically ductile, okay. Ductile means they have high ductility, they can withstand high strain, okay. And the examples, typical examples include polyethylene, polypropylene, polycarbonate, polyethylenes, propylenes, polycarbonates, polystyrenes. You will see typically the name is poly, right. So, it's like many ethylene molecules, many propylene molecules, many carbonates, many styrenes put together, okay. So, this is the category which is called as the thermoplastics. Thermosets on the other hand, they have a behavior, they have very large cross linking, large degree of cross linking between the chains. So, the chains that you see here, they have cross linked, they are linked by some other branches. So, these branches so as a result they are rigid. So, higher rigidity, because these cross links do not allow the chains to move as freely as in a. So, it could be the cross linking could be 10 to 50% of the total number of MERS. Okay, nearly 50% MERS can be cross linked, as high as 50% in a very heavily cross linked structure. So, they have higher rigidity, they are as a result hard and tend to be brittle, and they do not soften with heating. Okay, and they generally degrade at high temperatures, they decompose at higher temperatures. Okay. So, the examples of thermosets, let me give you some examples of thermosets. The examples are, for example, vulcanized rubber, many epoxies, and resins, for example, phenolic resin, polyester resins. Okay. If you are a metallurgist, you might have used the resin to set the sample, right? It is used for metallographic samples, and that resin becomes very hard after curing, and if you heat it up, it just degrades, it does not melt. Okay. Similarly, any epoxy, bakelite. Bakelite is another example of bakelite is used in a lot of electrical applications. It can withstand high temperature, but it decomposes at high temperature rather than melting, it does not soften. So, these are some examples of, so if I now, so polymers, since polymers have many formula units, many MERS, as a result they have a molecular weight, right. And there is a factor called as degree of polymerization. So, degree of polymerization basically is degree to which chains MERS attach to each other. So, if you have higher molecular weight, which means if you have, let us say, C2H4 molecule, this N is the degree of polymerization. So, higher molecular will mean higher value of N. So, higher the degree of polymerization, higher the molecular weight of polymers will be. So, if I plot, for example, as a temperature as a function of molecular weight of polymers, generally they have a behavior which is like this. Okay, let us say this is Tg, Tm, melting point is slightly higher than, so we can basically divide this in various regions. Let us say this is a region up to which it remains mobile liquid at high temperatures. At lower temperature, basically there are two regions loosely drawn. These are two regions. In the first region, it is basically a crystalline solid, Okay. In the second region it tends to become a partly crystalline, because if chains become longer and longer and the molecular weight increases, it is difficult for them to maintain the crystallinity because of cross linking and because of bending and flexibility of chains. So, it is partly crystalline. The crystallinity tends to decrease as the molecular weight increases, and at higher temperature it tends to convert into liquidy shape. So, for lower molecular weights, conversion from crystalline to mobile liquid happens at lower temperatures. At higher let us say range, somewhere in this range, it makes a viscous liquid, and that makes sense because if you increase the molecular weight, it becomes more and more difficult for chains to move. As a result, the viscosity of the liquid goes up, even the melt form, and then at very high this thing, it tends to become a rubber shaped material, and then in between somewhere it acts like here, it acts like a tough plastic. Okay. So, these are typically the regimes of polymers as a function of molecular weight with respect to temperature. So, at lower molecular weights, the crystalline solid or partly, or it has certain crystallinity, and it tends to convert into a liquid which could be mobile, which could be liquid with low viscosity or liquid with high viscosity depending upon the molecular weight. At very high molecular weights, the polymer is partly crystalline, and it tends to have a wider region between the glass transition and melting point. Between these two regions, it tends to act like a tough plastic, and before it becomes more rubbery at higher temperatures. So, these are you can say viscosity related behaviors of polymers as a function of temperature and molecular weight. So, we will stop here in this lecture, and we will cover the remaining part in the next lecture.